Okay, so today been talking. We'll talk about. Uh, oops, there we go. Okay. The fact that this was proved by Turing, I think probably we mentioned it in the very first lecture. Turing 1936. Satisfiability. This is what is called the Entscheidungs problem. This was one of the problems posed by Hilbert at the turn of the century, the very first problem. And Hilbert asked, given a mathematical statement stated in a formal logic, first order logic was what he had in mind. If you have a mathematical statement written in first order logic, is there an effective procedure that will look at this statement, evaluate it and say, yes, it's true or yes, it's false. And of course, Hilbert fully expected that there would be such an algorithm. Now, so this is Hilbert 1900, the problem. Now, Gödel 1931 showed arithmetical theories are undecidable. Basically, what does this mean? This means that the theory of n 0, well, you don't need any of that, plus times. Consider the structure of natural numbers with 0 addition and multiplication, that is undecidable. This is what was proved by Gödel. This of course left the question open, because what Gödel showed was, you give any inference system, any formal system, right, there will always be the sentences that are true, arithmetical sentences that are true, but for which you may neither have a proof nor a disproof. You may not be able to derive either alpha or not alpha as a theorem. But this only says that given any proof system, such a statement will exist, right? This still opens the possibility that given any formal system, there may be an algorithm that will look at a given formula and say, yes, alpha has a proof, or negation alpha has a proof, or neither, right? That's still left open by Gödel. Gödel only says there will be some sentences which will be undecidable, but maybe an algorithm can look at alpha and say, this one has a proof, this one has no proof, this one is undecidable, right? Undecidable in the system, neither has a proof nor a disproof. So that was left open, but people right then started believing that probably the answer is negative, right? There is no such procedure. The problem is, how do you show that there is no procedure, right? If there is an algorithm to do this, you present the algorithm. But if there is no algorithm, you must find some mathematical way of showing that there is no procedure, right? Do you understand the point? And that's exactly what Turing did. In fact, Turing set up the machinery of what we call Turing machines to solve the Entscheidungs problem. That's why his paper is titled on the Entscheidungs problem. So, and so of course it's a remarkable paper, probably one of the most remarkable papers of 20th century, because in just one paper he sets up the Turing machine model and gives a very intuitive explanation for why it's something that captures all notion of effective procedure. shows that there is a problem that it cannot solve, right? Gives a construction of a universal Turing machine, right? And proposes, gives actual demonstration of what we call the Church-Turing thesis, that any physically computable function is computable by a Turing machine, right? So it's a remarkable paper, and if you have not read it, please do, right? Easily downloadable from the net, and I must say that you can't claim to be a theoretical computer scientist if you have not read Turing's paper. I personally will come and object, right? So, yeah, so it's so, and he's a young man writing out there, right? And uh, in his 20s, very naive. You should, he really says if a mathematician were to sit down and this thing, how many symbols would he need? A finite number of symbols will do so much paper you will need, that you can think of as a. So the entire thing is motivated by in an everyday language, right? It's not something, and remarkably naive but beautiful and works perfectly. So basically, this idea that the halting problem for Turing machines is undecidable, and then basically that's used to show that the satisfiability problem for FO is undecidable. Of course, and so now what I want to do is to not, we can do a direct Turing machine reduction and show that satisfiability problem, if you know what it means, is co-RE, right? That is, that given any Turing machine M, I can construct a first order formula alpha m such that alpha m is satisfiable if and only if m does not halt on the empty string. We can prove this. This basically means that the problem is co-RE, if that means anything to you, that the complement is recursively enumerable. The halting problem is exactly what gives you recursive enumerability. This is a co-RE. If you don't know it yet, you will know it at some point, and I don't know if you have seen these things at some point. Have you? You're just about looking at these things now, or? Yeah, okay. So for first order logic, you know that if you take val, the set of valid formulas of FO, this is RE. Is this clear? The set of valid formulas of first order logic is recursively enumerable. Why? Because we have given a complete axiom system, right? So the theorems of the Hilbert system, right, can be churned out, right? There is a Turing machine which, you have the axiom system, so, and you have only one inference rule that we had, right? You remember? And given any finite sequence of formulas, it can check that it's a proof, right? So just enumerate all the formulas and check if it has a proof, right? So that's easy, right? Just churn out all the proofs. So this is recursively enumerable. Now we are talking about SAT, right? Set of satisfiable formulas. Now if SAT, if this was also RE, what would it mean? Both would be recursive, right? A set which is recursively enumerable and its complement is also recursively enumerable, then it must be a recursive set, right? So if SAT were RE, both would be recursive. So this says that if you prove this, this says it's co-RE but not recursive. Yeah. So, sorry. Yeah. Satisfiability is co-RE. Yeah. Validity is RE. This is the thing. Anyway, First, right now we are mainly interested in saying that it's undecidable, meaning it's not recursive. There is no effective procedure. That's all that I'm going to do. There is a lot more to this, and maybe we can take it up later. Now, I'm not going to do a direct Turing machine reduction because I want to do slightly different reduction, because it's something that's useful in many, many different contexts. And Ananya, in the Theory of Computation course, did you guys discuss the tiling problem, the domino problem or tiling problem? And okay, there is a closely related cousin that I'm going to talk about. And so the problem is called the coloring problem. Okay, what is the coloring problem? An instance of the coloring problem is given by where C is a finite set of colors and R and U are functions from C to the 2 to the C minus the empty set, and C naught belongs to C. So, what is the coloring problem? You are given a finite set of colors and two functions which you call right and up. This to any color, if I take any color, to the right of any color, which are the colors that you can have. And up function says, if you have colored a point, above it, what kind of colors you can get. We will just formally define that. A solution to the coloring problem, a solution to delta is a map from the plane, the positive quadrant to colors. You are supposed to color the entire positive quadrant, right, n cross n, such that obviously this is the origin constraint coloring problem. Actually, these things don't matter, but we'll put it in. And for all Mn belonging to n, what is it that we want? Yeah. Which pen should I use? All of them have something at the end. N plus 1 belongs to, C0 is a member of C, just some color that you are told. You are told that the origin should be colored by this particular color, and then obvious condition that you will have, the color that you assign to the point Mn plus 1 should belong to the right of chi Mn. And the color chi m plus 1n should belong to up set of, yeah, makes sense, right? Basically, you are supposed to color the n cross n. You have been told what you should do for C0. Now, 0 0 you have colored. So, this says 0 1 and 1 0 you have been given the constraints. You pick some color C1 here and C2 here, and then remember now, once I have colored 0 0, this is C0, so you pick some C1 and you pick C2. Now this automatically says that the right of this and the up set of this should have some intersection, right? Otherwise you are dead. You have to come back and try. This is the idea. Yeah, I pick some color here and I pick some color here. So this should belong to the right of C0 and this should belong to the U of C0. And once I do that, the intersection from the right of C2 and U of C1 should be non-empty. Then you pick one of them and you keep on doing this. So in a consistent fashion, in such a way that you get a coloring of the entire n cross n. This is the idea. This is a coloring problem, and we can show that this is undecidable, right? That
sir, C1 and C2 are any random colors?
Whatever, it's up to you, right? You want a coloring of from n cross n to C that satisfies these conditions. That is the solution, that's all, right? Is it clear? Now, so here is an exercise which has nothing to do with this course. So, but it's a TOC exercise for you. Exercise, show that this is a very nice exercise. Please try it. Yeah. And so this is an undecidable problem, right? And it's a very nice problem to think about because it's a simple combinatorial problem you are given, right? I mean, literally you can give it to children, right? Except of course you don't ask little children to tile n cross n or color n cross n, but you give a finite bunch of colors and grid points and say, hey, right, this is what you are supposed to do, and you can have a little video game which says, these are the possible colors. You pick one, boom, you can't do it now. So backtrack, keep doing that, right? Kind of problem that you would think of, and it's, you can show that this is undecidable, right? So it's undecidable exactly as by reducing to the non-halting problem of Turing machines. And you can guess that it's as hard as the non-halting problem, right? Because this thing goes on forever, right? So, any idea how you would do some reduction like this? How do you expect to code up Turing machines using this? Any idea? Does not halt on the empty tape. So the way to think about in these things is that, say, take a row, right? Take a row, think of it as a configuration of the Turing machine, right? And one row above is after one step of the Turing machine, right? So you have the Turing machine, and then it takes one step, goes like this, right? This is how you construct. Of course, and remember, you are allowed to construct delta m. You are allowed to define the right function and the up function. You have to do it carefully so that you actually code up the computation of the Turing machine. So if the machine doesn't halt, you will actually build a solution to the problem. And what you want to show is that I have defined it correctly in such a way that if I get a solution to the problem, I can read off a computation of the Turing machine, right? So, yeah, yeah, Shapna.
Sir, shouldn't that where you define number 2 for all m and n element of R, shouldn't that be the first one be up of x m
Yeah, I never get this right? So you're the mth row, the n plus 1th column element, no, this is okay, right? This is okay. 0, 1 should be to the right of 0, 0. Yeah, this is 0, 0. This is 0, 1, and this is 1, 0. Yeah, this is the mth row and nth column. Yeah, I always get it wrong, so I have to. It so happens that I got it right, so no big deal. I mean, whichever is the correct thing, put it in, right? Yeah. Okay. So now let's see how to code it up in first order logic, right? So now what we will do is, given any delta, we construct or we define alpha delta in FO such that delta has a solution alpha delta has a model. Yeah? Is it clear? This is how you do reductions, right? Once you know this problem is undecidable, take that and reduce satisfiability to this problem. And since we know that, yeah, suppose now this immediately shows that satisfiability problem for FO is undecidable, right? Why does it show that? Suppose there is a decision procedure for first order logic. Now what will I do? You give me any instance of the coloring problem, I will construct this formula and use that procedure. That would work, right? That will be a decision procedure for coloring problem, which we established is undecidable. So this is how the direction, the reduction always goes this way, remember, yeah? So now the question is, I have to decide what is the vocabulary. I am given delta, now I have to use, so I have to pick a delta, a vocabulary such that I can write a formula alpha delta. Now what vocabulary would you choose? Remember, I am trying to code up a coloring of the plane. What are the critical things that are there in this, in the expression of this problem? Look at this. Here I have a +1. This is important. So I need a successor, right? I need a successor. So I need two coordinates. I need to move in two different directions, and I need to be able to talk about successors in each direction, right?
Two titled functions.
You can use functions, you can use relations, what have you, right? Is it clear? So one possibility, so would anyone like to suggest a vocabulary? So we have language. First, constant symbols.
A set of constants.
Yeah, but what constant symbol do you want?
So elements of C, like
I know.
we have finite set of constants.
Yeah, but we have to decide a finite vocabulary. So I'm asking which one.
Yeah, C1, C2.
No. I want some particular thing so that we can code up. Is there any constant that is there that we need? Remember, C0, 0, right? So notice that the colors themselves are not constants. It's a coloring of the plane. The coloring is associated with a point. You're going to have elements of the domain, right? Remember, what kind of structure do you have in mind? N cross n, right? Remember, you want to talk about points on the plane, and those points are going to get some color. What does that mean? So with each color, you don't want a constant. What do you want with a color? So C is going to map to what for us? For each color, I want a unary predicate. This will tell me all the points getting that particular color. Is it clear? This is how we have to think, right? So colors are not constants at all, Chopin, right? But there are finitely many colors, so it's fine. I'll choose finitely many unary predicates to talk about the colors, right? If you have given me red, white and blue, I want to say red is a unary predicate, right? All those points that are colored red, all those points that are colored white, all those points that are colored blue, all saffron, whatever nonsense, yeah? So that's clear. So I want some, so I'm going to have some this, and here I will have unary predicates. one unary predicate for each color. Yeah, what else? But what constants do I want? Among the 0, right? Yeah, now 0, comma 0, where is that coming from? There is no comma structure. That's in your head. As far as first order logic is concerned, a domain is a domain, right? We can only talk about elements of the domain. So maybe I can talk about a 0 element of the domain, right? And then
which maps to 0, 0.
Which maps to 0, 0. So the 0 element of the domain that you have in mind, the constant symbol 0, maps to the origin. That's your intended interpretation. That's fair enough. And then what else do I have?
Functions, binary functions.
Binary function for what?
R and U.
R and U I certainly want to use, right? But R and U, do I need to put it in? This map is actually given to me, that R and C map, yeah? R is a map, R and C are mapped from C to 2 to the C. Of course, I have to, I am given already that it will be non-empty, so every color is mapped to a non-empty set of colors, right? R is like that, U is like that. Yeah, so we may need it, let's keep it. But what else do I need? Something that I critically need. What is that? I need to be able to talk about moving in along the x-axis and moving along the y-axis. Moving in two different directions. Yeah?
Successor functions.
Successor functions. So I need successor functions, but not one. So I need two. So let me call it. In fact, I'll write it as right. I need a right successor and I need a vertical successor, a horizontal successor and a vertical successor. Is this clear? I have a point in the domain, and along with every point in the domain, I want a right successor and a upper successor. And of course, I want the predicate symbols. Do you need anything else? Well, we want to do the coloring, right? The coloring has to actually assign a color to every point. So, yeah. So, this unary predicate is going to, well, we don't need anything more for now. Okay, we'll see what we need. So, I think this is the vocabulary that's clear that we need, right? Because there is a 0 here, so I need to talk about the 0 point. This refers to the right and up, therefore I need to talk about the successors, and the coloring has to be defined, and I have a unary predicate that collects points. So let's go ahead with it. If we need something extra, in the coding we find something we need, we put it in, right? This is how we should do it, right? Is it clear? Any question? Okay. So let's write the formulas, what my formula will say, right? First thing is, so going to have, first I have to write that it's actually a coloring, right? So this is something that we need to write. By now you must be used to it. For all x or over C belonging to C, every point must get some color, and you shouldn't get two colors, right? The point should not get two different colors, right? And over C prime not equal to C, not P C prime of x. Is this clear? This says that if I put together all the PCs, I get a partition of the domain. So what is important for you to realize is that the two-dimensional structure is all in our heads, right? The formula only knows, this is a first order formula, it knows that in the domain there is something going on. Yeah. Okay. 2, and this is simple. Whatever is the C0, that's a unary predicate, and that 0 must belong to that, right? The 0 element should belong to this set. So that's clear. And the next condition which we have here, now we have these two successor functions, right? Now what is the most important criterion of the successor functions that we must have? Firstly, every point must map to something, but that being a function, I don't expect any problem with that, right? Now this being a function, on the domain, every element is going to map to something, so that's not an issue. But what more? What is the critical property of the successor function that we need? When I started telling you how do you start doing the coloring? It's clear that the 0 point is going to get the color C0, and after that, it must belong to the right and the up, right? Those conditions. So we must write down those conditions. So let's write them for all x. Yeah. Once you have colored and over C belonging to C, the moment you have colored a particular point with color C, what should you have for, what is the consistency condition? Exactly what is given here, implies R over C prime belonging to R of C, P C prime, right successor of X. The right successor of X should get one of these colors, right? And R over C prime belonging to the U of C, P C prime, and some brackets have to be completed. Yeah. This takes care of the conditions that we have written there. Once you have colored a point, then the right and the up should come out correctly. Is it clear? I mean, you have no choice. Huh? This is a condition that is given in delta, you have to put it in. Are we done? Now let's get back to how we said we should do how the child is going to do the coloring, right? You are told how to color the origin. The grid paper is given to the child. So origin is done. Now 0, 1 and 1, 0, what is going to happen? Some choice will be made, right? Let's say 0, 1 gets a color red, 1, 0 gets a color green. But now to the right of green and to the up of red, you will have two sets, you have to look at the intersection, right? That must get a single color, right? That intersection firstly must be non-empty and you have to pick one and put. Where is that coming in? This is because you have drawn the grid, right, and given to the child. But who says that this damn thing forms a grid? The right successor and the up successor should form a grid, right? Are you with me, Siddharth? I have said that there is a right successor and an up successor, but they can go like trees, no? Why should they come together and form a grid at all? So I must say that. So for all x, for all y, right? If I start with x, right? And so in fact I think probably I can write it like this, just check that it's correct. The up successor of the right successor of x equals the right successor of the up successor of x. This is the grid condition. For all x, for every x, right? The right successor, the up successor of the right successor is the same as the right successor of the up successor. The diagram commutes is what people like to say, right? This forces the grid. And that's it. That's really it. Yeah? Because once you force the grid and the color C0 is given and you have written this consistency condition and you have said the coloring is proper, if you like, you have said it all, right? Pretty much all the information that is there in delta is now this. We still have to prove, of course, that delta, what do we need to prove? Delta has a solution. Okay. How does the proof go? Suppose delta has a solution, right? Then I have to show that this formula has a model. What is the model for this formula? A model for the formula is a domain with an interpretation for each of these and an interpretation for the colors in such a way that it satisfies all of them. Tell me the interpretation. What is the domain? N cross n. What is the interpretation for 0? Origin. What is the interpretation for this function? For any xy, it will map to x comma y plus 1. This will map any xy to x plus 1 comma y. What is the color? PC, exactly chi of mn, right? PC is the set of all mn, right, such that chi of mn equals c. That's absolutely the model. That's the structure. This is a sentence, right? There is no free variables anywhere here, right? PC0 of 0 is true because we have been told that chi satisfies. This is a solution, right? That's the chi that we are using. So C0 will certainly belong to the interpretation. I mean, the origin will belong to this, and you check that all the conditions are satisfied. And this is how it must be because we took that to mean this, right? So this is a completely straightforward thing. Please check, write down and check the details. Make sure that whatever I am saying is true. And of course, the grid property is satisfied because I started with n cross n and that is indeed a grid, and so there is no issue. Yeah? Right? This is x plus 1, y plus 1 equals the right successor of, all the, sorry, I'll just get confused if I say it, right? I'm sure this picture comes out right. Yeah? What about the other direction? Other direction is non-trivial because the model that you have got may be some weird model, right? I have to say that from whatever model you gave me, remember the model has goats, I always say, right? Model has some arbitrary elements, I have no idea. It's just that I am given these functions, right? So now what you should do is, from the fact that you've got a 0 element and you've got this, right? You have to give a map from the elements of the model. You have to give a map, let me call it H, from whatever is the domain that you have got in your model to n cross n. Yeah? That's what you need to do. Do you realize that? Because you are given an arbitrary model, now I have to map and we have to show that this is a this basically embeds D into n cross n, right? D might have all kinds of elements, right? I don't particularly care. What I want to say is that n cross n is embedding. There is an embedding of n cross n sitting inside D, right? And that it will, because remember, these are functions. The joy of functions is that once I have origin, right, it has a right successor, it has a up successor, right? Whatever those elements, I'll call them 0, 1, 1, 0. How do you do this? You do this by induction, right? You do this by induction and use the fact that at every point of time it is consistent. So the way I would do it, for instance, is to first build the rows, right? Build row by row, right? Build row by row, build column by column, build diagonally and fill out, it's up to you, right? There are lots of ways of doing it, but it's a very nice proof. I really like this kind of proofs, right? So show that n cross n is sitting embedded in this, right? And then now comes the colors. That part is completely straightforward, because these things make sure, this makes sure that PC is, it's a partition, right? Once it's a partition, I just have to define the coloring. First you define the coloring as a relation, n cross n, right? Define it as a relation and show that what will you put for x, y, c, for let's call it r, x, y, c, what will it be? If and only if x, y belongs to PC, right? Whatever is the element here, you map it here, that will be x, comma y, and if that belongs to PC, you know that all the elements belong to one of the colors, right? So this will inherit that coloring, that's the point I am saying, right? And this ensures that it's a function and the consistency conditions are satisfied. I am not going to do this mainly because, as I said, the idea is very, very clear. It's a matter of sitting and working out and making sure that all the conditions are satisfied. Please do this, it's a very nice exercise, and yeah. But if you have any questions, please ask me. Yeah. Remember that this is not the model, that is the important thing to remember. When you say alpha has a model, the model could be any creature, right? So you have to, and this is always a nice way of doing these things, right? I should be able to show that. Now there are various ways of doing it. One way is, I said H is a map from D to n cross n, but you can also think of it as H as a map from n cross n to D to show that it's an embedding, right? It's up to you, right? Think of it as a many one map and do this, or think of it as a isomorphic embedding inside D. N cross n is isomorphically embedded inside D. That's also possible. So there are, whichever direction, it's a matter of consistently doing it, right? The point is to consistently define that map and show that the colors are all inherited, and what you get is a function, and that function actually satisfies these conditions. The formulas are written carefully enough so that this is not a problem at all, okay? I hope the idea is clear, right? The advantage of doing it this way is that you separate out the Turing machine coding problems, right? And if you start thinking about it, there's not much of a difference. You are doing Turing machine coding. Remember, what does the Turing machine do? It moves right or left, right? And one step of the Turing machine is going to move it up. And remember, in a Turing machine, it's like this Tetris game, right? It always looks like this. At any current cell, right? If you are examining a cell, either you modify that cell, or you move left and modify, or you move right, right? At any point of time, that's all there is to it. The rest of it will continue to be the same. Whatever is here will continue to be here, just copy it. That is also a consistency condition of a right and up condition. That's about all that's going on, right? When you actually do the proof of the reduction of halting to this, you will be following pretty much the same kind of logic that I am talking about. But it's nice to do it. That's why I'm saying separate it out into 2 steps and do it, and it gives you a kind of nice exercise into thinking about Turing machine computations, as well as about how the this reduction goes as well. But writing formulas directly from Turing machines is much more messy, right? Much more messy to talk about cells and tapes, and you have large vocabularies. It's a bit of a pain. Okay, so either that or like if I don't know, you can talk to Prakash. If I'm sure he'll take up tiling problem at some point. Tiling problems are really beautiful problem. Tiling and coloring are very closely related. So any one of the problems and you can code up into this. Yeah. Okay. Should I? Is there any more on this? Can I move on? Now, the immediate comment that we must look at is this vocabulary. So, what have we shown? We have shown that the satisfiability problem for first order logic is undecidable if your vocabulary has, as long as your vocabulary has at least one constant, two unary functions and an arbitrary number of monadic predicates. So, we have shown undecidability. Oops. Undecidability of FO for one. By the way, this constant symbol is really a distraction, right? This coloring problem continues to be undecidable even if you don't put an origin constraint. It's just that's another coding. So we can always get rid of that constant symbol. So that's not a problem. But what we had was two unary function symbol. Let me call it FG, two unary function symbols and an arbitrary number of unary predicates. Yeah, this is the vocabulary. We have shown undecidability of first order logic for a vocabulary that has got two unary functions and an arbitrary number of unary predicates. Okay. Now, it turns out that whatever you do with unary functions, you can always do using binary relations, right? Because saying that a relation is a function in first order logic is very easy, right? Because you will say for all x there exists y such that r x y, and then for all z if blah blah, you know, we do it in class 11, right? So it's clear that I can do this with binary relations, and I use this as a point and color, right? I use this arbitrary number of unary predicates to talk about colors. That also can be thought of as a binary relation, right? That a point gets this color. So actually, if you sit and do the work, you can do this entirely with arbitrary many binary relations, or if you like, arbitrarily many unary relations. I am saying forget the functional vocabulary. You can go to a relational vocabulary and show the undecidability for R1, two binary relations. Yeah, I am saying the undecidability proof we can tweak and do it with two binary relations and an arbitrary number of unary relations. Right? This is what I have written here. No constants, no function symbols, arbitrarily many unary relations, that is predicates, sets, and then two binary relations, and we can do this job. And in fact, you can actually choose an order relation here. Rather than successor, you can choose an order relation less than 1, less than 2, because from an order you can always define successor in first order logic, right? You know that, right? You can start to write x less than y, and there does not exist z such that x less than z and z less than y to talk about. So that's easy to say it's a function all that. So why should we think about such things? You must look at the minimal vocabulary that is needed, right? In general, to show something is undecidable, whenever you prove a negative result, you must choose as weak, your assumptions must be as weak as possible, that's why. Yeah, and turns out that you can go even further, and in fact this was shown by Gödel that you can a single binary relation will suffice. You don't need to have that's difficult. Okay, so that requires more complicated coding. I am not going to go down that, but yeah. So this is shown by Gödel. That one binary relation suffices, and in fact, that thing is so complicated that in fact you can fix the number of unary relations and a binary relation, and it's already undecidable. Okay. So the coding gets more and more nasty. Like you have seen with Turing machine codings, right? Universal Turing machine. Have you constructed a universal Turing machine yet? You have not done the construction yet, or okay. If you have not done, you will do it at some point. There is always the question of what is the smallest number of states, right? State symbols with which you can construct a universal Turing machine. Yeah? And what do you think is the smallest number? Remember, a universal Turing machine should be able to simulate any Turing machine, no? How many states do you want for? Okay, and people have really battered this down. Okay, if you can construct a 7-state universal Turing machine, you are really doing very, very well. Okay, if you can do it with 4, you are a real dada. Okay, so and this is the kind of point, right? To the coding gets really complicated as you know, but somebody should enjoy doing this kind of thing, right? Bring it down to the most minimal thing possible, right? So and of course Gödel is boss with codings, right? So yeah, so this gets very complicated, but it's very worth it. Think about it and how it goes. I want to. There is a lot more to do to discuss there, but we'll get to it later. I want you to realize that look at the kind of quantifiers we used. What quantifier did we use?
For all.
That's it. That's it. So what is very nice is that with 2 unary functions and arbitrary unary predicates, just the universal fragment is undecidable. What do I mean by universal fragment? Not all formulas, only formulas which have a string of universal quantifiers followed by quantifier free formula. That's all. Gurevich in 1976 brought this down to get rid of even this also. So Gurevich 1976. And then he showed that in fact you can replace this by just for all star of no constant symbols, a single binary function and that's it. So this is in mirroring with this. Either you go for a single binary relation, right, and or you can go for a single binary function and just the universal quantifiers, nothing else.
Okay,
and
for all star?
For all star is any number of universal quantifiers, right? I think I have used only one, right? Yeah, so there is only one, so I don't even have to look at. Yeah. However, here when you go, the moment I go to relations, note that your quantifiers are going to increase because you have to say it's a function, right? Remember that I'm getting away with just a universal quantifier because a lot of stuff is hidden in functions here. Otherwise, I'll have to write for all x there exists y, blah blah, right? I mean, even to say it's a function, right? Coloring is a function, I have a lot of work to do. So we'll get to that. But the point is that function symbols are killing, right? It's not a surprise that when I talked about EF games, we're doing this lot of finite model theory, it is all with the relational vocabulary, right? Relational vocabulary you can do a lot more. Function symbols, the moment you've got two unary functions or one binary function, you are dead, right? And just the universal formulas are enough. Of course, the universal formulas smuggle in existential formulas because of the, remember, if I were to write this as relations, I'll be writing for, I started writing in fact for all x, for all y, right? And I must say for all z such that, if there exists z such that right successor of x is y and up successor of x is w, right? Then there exists etc etc. So you will see that the moment you start this thing, that makes sense, right? How do you say a relation is a function? For all x there exists y such that r x y, and for all z, remember that this is of the form for all x there exists for all, right? So at least two quantified alternations are needed to talk about relations being functions. So it's not as simple when you go down to relational vocabulary. But there is one more problem that I want to mention, and after that we'll get back to this. We'll keep the I want to show that, and in fact this is (1950) or a little bit later, I don't remember, maybe 50s. Finite satisfiability of FO is undecidable. What do we mean by that? What is the problem? You are given a formula. I am interested in asking, is there a finite model? Sit. I just want to know if, now clearly this is RE. Why is it RE? Given a finite vocabulary, I have only a finite vocabulary, right? The set of all finite models is enumerable, right? I can enumerate all the models by its size. The set of formulas is enumerable, right? So since the class of finite models is enumerable and the class of this, the product is enumerable. So given a finite model and a formula, of course it's recursive to check whether alpha is true in that model, right? Is it clear? I can enumerate the models, enumerate the formulas, and diagonalize to get a enumeration of the product. Now, given any particular finite model and a particular formula, is whether alpha is true in that model or not, is we have already done an algorithm to do that, right? To check whether alpha is true in that. So that's certainly recursive. So clearly, yeah. Well, that is the point, right? There is an enumeration of models, enumeration of model comma alpha, right? So a Turing machine which doesn't halt, right, will just enumerate these pairs and each time say whether true, it will keep checking. Of course, if it finds, if alpha had a finite model, at some point it will stop and say yes, here is the model. But if alpha has no finite models, it will go on forever. Is it clear? Yeah. So it's clearly RE, but what the theorem says is that it's not recursive. Okay. So now we are talking about a reduction to something where we can't use halting, right, because this is about finiteness. But it turns out that this is undecidable as well. So we will show that this is not recursive. How do we show that? Well, we have the coloring problem, right? So the finite coloring problem an instance of the finite coloring problem is you are given a finite set of colors, write an up function, and two colors, C0 and C1. I'm sure you can guess what's coming. Can you? What is the solution to delta? A solution to delta is first a pair m comma n. So you are asked, is there a finite rectangle that is colored, right? Can you color a finite rectangle for me? A solution will tell me the rectangle is 0, 0 to mn, yeah, that is a rectangle. So chi of C0, 0, 0 is C0 and chi of mn equals C1. So chi is a map from what to what? 0 to m, 0 to n to C, such that the origin is colored C0, the other end of the rectangle is colored C1, and it is not for all mn, right? So this is the thing. Oh, I have written it as mn. I should have called it something else. UB. Yeah, for all m belonging to 0 to u minus 1, n belonging to 0 to v minus 1. Yeah, exactly the same thing. I mean, it can't be much else. I mean, once you say it's the same kind of thing, instead of asking for a coloring of the entire positive quadrant, you are asked to color some finite rectangle, right? You are allowed to choose, but this is where, what do they call, what is that song? Freedom is just another word for nothing left to choose, sort of thing. And once you are condemned to choose, right? How do you hope to find this rectangle? Remember that the search is unbounded now, right? But that's exactly what halting problem is about, right? So in fact, learning theory of computation, what is very important for you is to start smelling out these things, right? Somebody gives you a problem like this, right? It says, you are free to choose mn, right? You find your own mn and tell me. But that's exactly what halting problem is about, right? So it's not very surprising to see that this is exactly as hard as the halting problem. Okay, so that is the next exercise, is to show that given any Turing machine M, I can construct an instance delta M of the finite coloring problem such that M halts if and only if delta M has a solution. Yeah. So earlier we said M does not halt if and only if delta has a solution, where we had a coloring of the entire positive quadrant. This one, and the coding is very similar, the Turing machine coding, because once the Turing machine halts, what will you have? You will have the sequence of configurations, right? That will give you the rectangle. But of course, the coding has to be in such a way that reverse direction also, when the Turing machine halts, take that rectangle and you can code off, you can read off a solution. Everything is exactly as you would expect. So it's not a. Now let's get back to our first order logic. What's our vocabulary now? What is the big trouble now? The successor function was very, very nice to have.
So you have to stop somewhere.
You have to stop somewhere. And there will be boundary conditions where the damn thing will not have a right successor, but it is expected to have a up successor. Similarly, the top row will have right successors, but it will not have an up successor. So it's not a function, right? This is the main point. So we might as well have work with relations. Remember what I told you is that we have to work with relations. In fact, if I had been unkind to you, I would have done the coding entirely with relations and showed you. But it's more natural for the general satisfiability case to use functions, right? Okay. So we are condemned to use relations. So we might as well give up on no function symbols. So I'll have less than 1, less than 2, right? I should really write less than in the right direction and less than in the up direction. Okay. Which of course from this being first order logic you can derive a successor relation, not a successor function, a successor relation. That's really not a problem. Okay. What else do we need? We need of course the coloring. We need anything else? We don't know, we'll find out, right? If we need something, we'll put it in, that's not a problem. Now, from this, I do have this I'll use it in the formulas and we know that what they mean, right? I'm not saving on quantifiers and stuff, right? Remember that this will involve for all that exists for all. Yeah. Writing these things involves. Yeah. Okay. So what are the things that we need to write? So the first formula that we had, I have erased it. We'll have to redo the work. Let's do it. What do I need to do? The first one is exactly as before, right? For all x R over C belonging to C, Px of C, or Pc of x, sorry, and over not Pc prime of x. Not much choice here, we need to have it. Yeah, this formula remains exactly as before. What about 2? Yeah, this is also natural. What about 3? For all x and over C belonging to C, Pc of x implies. The first one I can't say the successor has this because I don't know whether it has a successor or not. So I must write for all x, for all y, right successor of x is y implies. Is this clear? What does the right successor of y tell you? R over C prime belonging to right of C, Pc prime y, and up successor of x is y implies R over C prime belonging to u of C, Pc prime y, and one more bracket. Yeah, this is the natural modification of the formula that we had earlier. I hope there is no controversy in this, right? Okay. Now we have to say that there is the grid condition. We have to talk about the grid condition, and even more fundamental, I have to say that successors exist, right? So first, successors must exist when we need them. When do we need them? Whenever I am talking about something that's remember I have to say, and now comes the end condition. I have to say there is a point which is labeled C1, remember, right? And I have to say until you get to that point, successors exist. Is this clear? Yeah? So I have to write for there exists U and so this says that I am starting with 0, that says there is a point that is labeled C1, and until I get to that point, I see the right successors and the up successors, and they form a grid, right? That's what I need to write. So I need to write for all x, x is less than right u implies, yeah, this is an order relation, right? Remember, it's an order relation. That means that the left component, that's how we have read it, right? It's the x component for, right, the x axis for this is less than the x axis for u. So that means that it has a right successor, right? So I want to write there exists z, there exists y such that s right of x is y, and there exists y u, sorry, and then I think this is enough. Yeah, this says that as long as I have got, I am lying to the left, somewhere to the left of u, right, then I can move right. And that other one says that somewhere, if I am, as long as I am somewhere below u, I can always move up. We still have to write the grid condition. The grid condition is separate. Where shall I write it? Maybe I shall. This one I can get rid of. So I'll write it as 2, 5. For all x, for all y. Yeah. If I am sitting here at any point of time, if I am for all x, for all y, for all z, this is what I want to say. If I am sitting here x, and to the right I see y, and to the right, up above I see z, then there exists a w such that these two come together. Yeah. For all x, for all y, for all z, if I see a sideways branching, right, at x I see y to the right and z above, then there exists a z such that from the right of z I see w, and from the above y I see w. Yeah, such a thing exists is what I want to say. So this is right successor of x is y, and up successor of x is z, implies there exists w such that right successor of z is w and up successor of y is w. Some brackets probably. So this talks about the grid condition. Okay. And that's it. Of course, where it's only where it exists that this is said, right? So if this relation doesn't hold, of course there is no condition, right? So for the boundary cases, for the boundary this is not a problem, right? It is not expecting anything to happen because one of them will actually be false, right? If you are in the top row or in the rightmost column, one of these two things will be false, and you have no problem with that. This only says that if I am talking about an interior point where I can move actually right as well as up, they must come together. Okay. So now we have to show that the same thing, whatever delta has a solution if and only if alpha delta has a finite model. Same thing, if delta has a solution, which is the finite model for delta, alpha delta, the given, right? You are already given a solution, so take the rectangle, right? The m by n rectangle, m plus 1 by n plus 1 rectangle as it turns out, right? That's how I have set it up. Yeah, take that rectangle, and that is indeed a model, right? Because the interpretation will be exactly as you would say. The 0 is the origin. This is given by the less than on the right row coordinate, and this is less than on the column coordinate, and the coloring is given by the function. And it's easy to check that all the formulas are satisfied in this model. All the sentences are true in this model, right? What about the other way? Again, it's a bit of a mess. Suppose alpha delta has a finite model, right? You know that the model is finite, that's all you know. From that, by reading the conditions, we have to pull out the rectangle. How do you do that? Well, you start with 0, you know that there is a 0 element, right? And then you know that there is a diagonal, this element. So this one, there are many ways of going about it. I find it, when I did the proof, I find it more natural to do the diagonal, right? Basically you fix this point, first construct, right, whichever way, and then fill out, right? Because you know that this is less than, so there must be 1, and this must come together, this must come together, this, and so on. This is a very nice construction, inductive construction. Do it, you will really enjoy it, I assure you. Yeah, if you enjoy such things, I hope you do, right? So the other the problem is, if you start constructing freely, there is no guarantee that you will get to the one that leads you to you, right? So you have to, this is a the other one was much more free, right? You had the whole quadrant, and here I know that 0 0 is here, Mn is here. I need a walk to go from 0 0 to Mn to reach C1. So you must fix that, fix those elements, and then fill out whatever you need, because the model may have all kinds of junk. Remember, it's a finite model, right? It may have lots of trees branching out which don't come together at all, right? Who says it must have, right? Model will have all kinds of crazy stuff, right? So you must pull out the rectangle, and that is given by that function that I am talking about, right? And because remember, in this case, even the length m and n is not known until you come up with the walk and actually hit it. You don't know what is the m and n, right? This is just a model, right? So you have to read off the m and n from this walk. How do you get that? By this fact that it tells you where is this. This is a nice one. This is a very nice one. This actually tells you that there is always a successor, right? So then you find the right successor. Am I still below? Okay, then there is an up successor. Am I still below? Right? Keep going right and up, right and up, right and up, or up and right, whichever, and actually hit C1. Now the length of the path that you have constructed will actually tell you M and N, right? It's a very nice way of doing this, and then you can fill out, because the grid condition that we have written there will tell you how you can fill it out, right? So then you will get a map. Once you get a map, the rest of the proof is exactly as before, because remember that the consistency conditions are set up in such a way that the earlier proof that you had, right, for the infinite case can be just specialized narrowly. The rest of it goes through smoothly. But it's also a very simple and elegant thing, because you now realize that as long as you can force grids, right, this is a very powerful tool for showing problems to be undecidable. If you can force a grid, right, so if you actually do more finite model theory or whatever logics and decision procedures, there is this question about, for logics of computation, what exactly, first order logic on what structures is, decidable. Here we are showing undecidability of generally in first order logic, right? Maybe I restrict myself to model classes, right? What class of models, right? What class of model classes give you undecidability for first order logic? Grids, clearly grids is something that you get undecidability, right? So if, for instance, you were to look at, forget first order logic, you were to look at automata, right? Automata that run on words, you have various decision procedures. automata that run on trees, you have various decision procedures. What about automata that run on graphs, right? Now, a grid is a graph, right? Any class of graphs that contain grids in them, the emptiness problem for the automaton would be undecidable by very similar logic. So today, the kind of consensus, if you ask for automata that run on different classes of structures, what's the class of graphs for which emptiness is decidable? Well, anything that avoids the grid, right? What is that? Well, stated in terms of graphs. Well, graphs of bounded tree width. Graphs of bounded tree width is a very robust class. Algorithmically, there's a lot that's very interesting about them. So mainly because your trees can grow as widely as possible, but they, if they keep coming together, you have a problem, right? So that's the intuition. Okay, I mean, there's a lot of formal work to be done before you can get there, but I'm just telling you that. So that's why I wanted to do a proof like this, so that you understand the heart of. So even if once you can force grids, even if you are looking for only finite structures, right? Even if you are looking for finite structures, FO is undecidable. And the part of FO that we are using is very innocent, right? There's very little that's going on. It's just for all there exists, right? There's almost nothing that is, there is an existential quantifier, there is a for all there exists. And of course, for successor, in between, to say that it's a successor, if you actually unfold it, you will have one more for all coming in. So this is considered in terms of the class of formulas that we are using. This is in the relational vocabulary for all star. Let me just, okay. So now this you can specialize, you can bring it down to for all squared there exists for all. Two existential, there are three here, okay. Now all this can be specialized, okay. You can bring it down further. So on a relational vocabulary, this class is what you can show. No, I think you have. I'm not sure. No, I have to check it out. Yeah. And all this can be done with a single binary relation. As I said, that's a more complicated exercise. Now we have used two binary relations here, and the less than binary relation is given, right? So we have done everything with two binary relations and arbitrary number of monadic predicates. But okay, so yeah, so this is the heart of the undecidability of first order logic, and this started off a huge amount of work, and even before Gödel, in let me just give you a little bit of history, maybe 5 minutes, and then we are through. I'm not going to go into this, but just to tell you that this is a very interesting thing. And as I said, after this, people started looking at sharper and sharper. What's the borderline for undecidability, right? And so even before Gödel, all the way back in Löwenheim in 1915, showed that there exists star is decidable. If you have only the relational vocabulary, there exists star or for all star, right? Decidable means that and the complement, whichever. Yeah. Like we said, once you have function symbols, already for all is with a single for all, it's undecidable. Yeah. But if you have a relational vocabulary, if you only there exists star and just a sequence of existential quantifiers and then a quantifier free formula. Now that's not very difficult to see, because if there are k existential quantifiers in front, guess, right? So you can try make a guess and then go for the rest of it, and you can try to guess a model. And then also showed monadic FO is decidable. What is monadic FO? You have only unary predicates, no binary relation at all, right? So you only sets and this, right? No relation whatsoever. Yeah, and that is decidable. And this you can think of as, if you take formulas in monadic FO, right? You have a domain. What is monadic going to do for you? You can think of it as colors, right? If there are k predicates in your formula, right? There are k colors. You are talking about some coloring of the domain, right? Now, what you can do is to guess a coloring, right? And check that the formulas, are satisfied over it. And this is one way of going about it. It will actually give you a non-deterministic exponential time procedure, and that's, we can show, is in fact the lower bound. So this is all long before, right? In 1915, between 1915 and 1920, that was all done. So then people started looking at, and this is Bernays, Schoenfinkel, 1928, showed that there exists star for all star is decidable. Decidable without equality. Ramsay, 1928, showed with equality. Okay. So, what are these formulas? You are allowed one alternation. If you do the Skolem normal form, bring all the quantifiers together, right? So you have some prefix, quantifier prefix, and then you have. What you are saying here is that if you had only existential quantifiers, there is no problem. If you had one alternation, and okay, and Ramsay's paper in this is the one that I was referring to earlier. There is a lemma that he uses here. Look at what is there exists for all saying. There is a way, right, by which think of it as x1 to xn, right? So what he did was to give a kind of a partition idea, right? That there is one way of partitioning such that all the rest of them get some particular property, right? So this is what is the famous Ramsay's theorem, or what today is called Ramsay theory, what led to. So this is one lemma in trying to prove the decidability of this thing. It became, and as I said, Ramsay is another very, very colorful figure. Again, he lived until he was, he was hardly 30 when he died, I think 29 or 30. And he wrote 3 or 4 papers, all of which were deeply influential. As I said, in combinatorics, Ramsay theory and Ramsay's theorem is extremely important. And then foundations of probability, there is Ramsay. Then in group theory, so he did some 3 or 4 things, and that's all. And as I said, very, very young, very impressive figure. Yeah. And then, yeah, sorry?
So economics too.
Economics, that's foundations of probability for me. Actually, yeah, it's used in economics, but it's really foundations of probability. Yeah, it's the same thing. Yeah, absolutely. And then you had Gödel, Kalmar, Schutter, 1932 to 34, showed that there exists star for all, there exists star. Decidable without equality. And this is one of the famous papers for me, because this is the one in which Gödel, in a footnote, says, we have developed all these techniques, but similar things apply for equality. And then for a long time people tried and couldn't do the proof until Goldfarb in 1984 showed that class is undecidable with equality. So even Gödel can be wrong, right? As I said, it's one of the deeply satisfying things to know that, right? So, because Gödel is like super particular, and he's also like, leaves remarks and footnotes and various things like that, just casually, which takes like a lot of work to prove, right? And so in this case, Gödel was wrong, right? And it also shows that these things are very, very subtle, right? Many of these things are subtle. Have equality or not, have constants or not, can make a lot of difference, right? And yeah, so basically by 1940, what was undecidable was very clear. Like I said, Gurevich in 1976 came and showed, but by then it was already clear that I think Kalmar had brought it down to some 3 or 4 function symbols to do. He brought it down to 2 unary or one binary function symbol. So yeah, so the borderline became clear. So then started the question of with what prefix classes and what vocabulary can you get decidability. So this was called the classification problem, popularized by Tarski. Tarski proposed a host of open problems in 1940, which I think kept mathematical logic busy for pretty much like 50 years until 1980s, when everything was completely classified. So this is called the classification problem. There's a very nice book in IMSA library giving all the proofs and the complexity, showing what is undecidable with the weakest vocabulary, showing for every whatever prefix class with whatever vocabulary. So because you have to look at which kind of quantifiers you use, how many function symbols you use, how many relation symbols you use, how many monadic you use, all that for all the combinations. So for monadic function, monadic FO with over relational vocabulary, right? This is all relational. Rabin showed that monadic FO is decidable with arbitrary number of unary functions. That's one of the very, very difficult proofs. And so Rabin settled it in by Rabin, Shala, 1980s settled pretty much all of them. There were only few hard ones were left by then. So that's one of the successful projects of mathematical logic of the 20th century, the classification problem. And in model classes, theories, arithmetical theories, Gödel showed to be undecidable. So then came the question with addition and multiplication, it's undecidable. What about with only addition? Pressburger showed that with addition, first order logic is decidable. In fact, even monadic second order logic with addition is decidable. And Pressburger is another romantic figure in this. He did this. Tarski said it's worth a master's thesis, not a PhD. So, well, he enlisted in the war and he died in the war. So that is the only thing he did. And Pressburger arithmetic is another very beautiful piece of work. And so with addition it's decidable, addition and multiplication it's undecidable. What exactly can you add to addition that makes it decidable, right? So so that there is Cobham's conjecture which says that there is a power of 2 predicate that you add, that's exactly the borderline, but that's a conjecture. But Cobham's theorem shows that with some particular kind of modulo predicates, powers of 2 with perfect powers, it is decidable, and the conjecture says that that's a borderline. Anyway, so on arithmetical theories there is a lot. Tarski showed that with if you interpret over reals, arithmetic is decidable with addition and multiplication, and that even today has really beautiful applications. So, and then came the question about what about just an equational theory, Diophantine equations. This was the Hilbert's 10th problem. That was unsolved for a long time until Matyasiewicz showed in 1976 that that is undecidable. So Diophantine equations over reals you can solve, over integers you cannot. Julia Robinson showed that the integers are definable as a subset of rationals, plugging in 1 bit. So a lot of work got done in arithmetical theories. Abraham Robinson showed that algebraically closed fields is decidable. So complex numbers you can decide. And so now that has gone into a whole field of applications to algebraic geometry, differential geometry, lots of work has been happening there. What about combinatorial theories over trees, over graphs, like I said, over linear orders? A lot of work was done in basically in the 60s. And I mentioned the Buchy's theorem, that's over finite words, over infinite words also to show, because if you don't have order, right, if you take arithmetic with just the order relation, what is decidable? Anyway, so that's a whole, this thing, I gave a semester course called Decidable Fragments of First Order Logic. So it's worth a full semester, because with model classes, with different order relations, how many order relations can you have and get decidability? Can you get equivalence relations and get decidability? So there is a lot of beautiful material And some of this that I'm talking about is 21st century, in the last 20 years or so, right? So it's a whole course by itself, so I don't want to go into that. This is only to say that this is a refining the decidability and decidability results for various classes, model classes and fragments is a very interesting and important thing for theoretical computer science, because it has very tight relations to complexity theory. Okay, let me stop here. So next time, from Thursday, I want to take up a new topic, and that is a topic of something in between propositional logic and first order logic, right? So we have talked about first order logic and Boolean satisfiability. Are there logics in between which are nice? And turns out that there is a very, very nice logics, and we want to, for which logic and computation belongs exactly there.